Okay, is my screen is visible to you?
Sir, visible, sir.
Okay, right. Okay, so far we discussed about complex loading and how to evaluate the magnitude of principal stresses and also a maximum shear stress well in case of a complex loading is there on a component. So now today we'll see how we can approach for designing of a component when it is subjected to combined loading or maybe complex loading. So first we'll see some examples when you will have a complex type of loading. Then we'll go to the next step, that is how we can find or how we can design the components or machine components when they are subjected to a compound loads. We'll call it as compound load or combined load or maybe complex load also. So generally, if you take any machine component which is subjected to several types of loads simultaneously, so it may not subjected to only single load. If you take any machine component, so what you are observing, so they are not subjected to a single type of load. So it may be subjected to a combination of loads like what we discussed in the previous class. So, for example, if you take a power screw, the power screw is going to subjected to a torsional moment as well as an axial force. So generally these power screws are used in the power transmission. So whenever there is a power transmission, obviously it has to subject it to the torsional force. In addition to that, because of the friction at the screws or at the threads, so it is subjected to some axial force also. That means because of this torsional movement, you have a torsional shear stress, and because of axial force, you have a direct axial stress. So that means there are two kinds of load. Torsional moment is not same as axial force. So one is inducing a normal stress, other one is inducing a torsional shear stress. So then this kind of situation, what we can call it as, it is a complex state of stress in the component. Similarly, if we consider an overhang crank, it is subjected to both bending moment as well as twisting moment. So here also we know that because of bending, there is a bending stress, which is a normal stress, and because of twisting, there is a shear stress. Similarly, if we take another example, a bolts which are used to fix the bracket is subjected to both tensile as well as shear stresses. So when a bracket is subjected to some kind of force, then, because of force, there is a direct load, which is direct. It may be direct tensile stress or direct normal stress. And then, because of eccentricity, those bolts are subjected to the shear stresses. So, here in this situation also, these bolts are subjected to a combination of stresses or complex state of stress. Then, if you consider a crankshafts, whether it is a propeller shaft or connecting rod, they are also subjected to the complex loads because of variation of the load. And not only that, so because of the eccentricity of the transferring load from the cross section of the component, it is subjected to both bending moment as well as twisting moments. In addition to that, they may be subjected to normal transfer shear stress also, normal stresses as well as transfer shear stress also. Like this, when a component is subjected to several types of loads, combined stresses are induced. Like that's what we are discussing now. While bending moment causes bending stresses in the transmission shaft, whereas torsional shear stress will induce because of torsional moment. So now the failure of these components. Now, if you want to design the components to withstand these combined loads, then generally first we need to see what is the failure of these components, how they are failing. Then based on that we are going to design the components. So generally the components are failed in two ways. One is by elastic failure, other one is yielding and fracture. So we already discussed, I think, about these types of failure. This elastic failure is nothing but the excessive deformations in the component which will cease its functionality. So that means because of the excessive deformations in the structure or in mission element, so the machine is not able to perform as its intended function. So then I can call that kind of failure as a elastic failure. The other one is yielding. Yielding is nothing but so deformations when the stress induced in the component is exceeding the yield strength. So there is a plastic deformation will be there, and that plastic deformations are very large. So then that may be also considered one of the failure. Then the last one is a fracture. So fracture is nothing but brokening up the component into two or more pieces. We'll call it as a fraction. So generally, but in all our design courses, we don't bother about this yielding and fracture. We'll talk about only this elastic failure. So that's why whatever theories of failure we are discussing today, they are applicable or they are based on this elastic failure only. So we are not talking about yielding and fracture. We will talk about only elastic failure. Means so the component is subjected to excessive elastic deformations. So the deformations are within the elastic limit only, but there is a excessive deformation. So because of that, the component may not perform its intended function. So then we call it as a elastic failure. So that's what I written here. Elastic failure results in excessive elastic deformation, which makes the machine component unfit to perform its function satisfactorily. So that means whatever the intended function is there for that machine, it is not able to perform its function. So then we'll call it as that kind of failure as elastic failure. Yield stress results in excessive, okay, in case of yielding, that is nothing but a plastic deformation like I already told to you. So when the stress exceeds the yield point stress, then there is a plastic deformations are there. So whereas in case of fracture, it will result in breaking the component into two or more pieces. So that we call it as a fracture. So in theories of failure discussed in this article are applicable to the elastic failure of machine component. That means whatever theories of failure we are going to discuss, they are applicable only for elastic failure of the machine components, not for yielding or not for fracture. So then the design of the machine component subjected to combined loads should be related to the, okay. So now here what we need to do is I want to design the components for a combination of loads. So then to specify that whether they are going to fail with the given load or not, what we need to do is, so one thing what we have to do is we need to conduct the experiment. So under actual conditions. So that means suppose I have a component, just like we mentioned some of the examples earlier. So I have a power screw which is subjected to a tensile loads as well as a twisting moment. So now whether that power screw is able to withstand that those loads or not. So how I can know that? Just if I conduct some experiment for that, so then I can say if the component is failed, I can say it is not withstanding the loads. If it is safe, if it is not failed, or if it is performing its function, I can say the component is safe. So but here the problem here is, okay, if it is only one component or one type of load, I can conduct the experiments. But if you take in practice and in practical conditions, there may be have different types of components, and also the loading conditions are also not similar in all the conditions. The conditions are also similar. So that means in order to estimate whether the component what I am designing is going to safe for the given conditions or not, so conducting experimentation for each and everything is going to be very, very difficult, or even it is not possible also, because it will experimentation will involve lot of costs are there. You need to set up the experimental setup for each and every situation, and then you need to carry out the experimentation. So there is a lot of what you can say cost is involved in experimentation. So therefore, and also practically it is not possible to conduct experiment for each and every case of a load case, each and every load case. That means in one instant I have one kind of load, in another instant I have another kind of load. So therefore, it is not possible to to carry out the experimental investigation for each and every type of loading. So therefore, what we need to do is, so if that is not possible, then how I can arrive when a component is subjected to a component is subjected to a combination of loads. So then, is there any mechanism to identify that so that I can relate these stresses to the material properties? So that is going to be done. Only possible way of testing is generally the people will do either tension test or stress test only. So most of the cases, the 10 will get the material properties from the tensile test or simple tension test, where we'll get the yield strength and ultimate strength. Maybe if you want, you can get percentage elongation or percentage of reduction in area like this. These properties will get from your simple tension test. So, is there any possibility of making use of those properties what I am getting from the simple test to relate this to this complex loading or the state of stress which is generated because of this complex loading? If that kind of such possibility is existed, then I can design the components when they are subjected to combination of loads, even with the data of simple tension test. So in that case, simple tension test is going to be very easy, and we can easily conduct for the tension test for any type of material for anything. So therefore, we need to see some mechanism which can relate the state of stress in a complex loading to the properties which are available through the simple tension test. So then we can design the components. So the relation between these two is given by these theories of elastic failure. So that means these theories of failure will relate the data of the data or the stresses because of this combination of loads to the properties which are evaluated based on the simple tension test. So that means here our experimentation is we are going to do only simple tension test, and we'll take the results of the tension test and we'll use those results to design these combined components which are subjected to the combination of loads through these theories of failure. So that is the importance of these theories of failure. Okay, so that's what I written in these slides. The design of machine parts subjected to combined load should be related to experimentally determined properties of material under similar conditions. So then that means if you want to design a machine component subjected to combined loads, it should be related to the experimentally determined properties of material under similar conditions. So however, it is not possible to conduct such tests for a different possible combination of loads and obtain mechanical properties. Like I mentioned, it is very difficult to conduct all kinds of tests on the components, so which will be very costly also. So therefore, in practice, what they will do is, in practice, the mechanical properties are obtained from a simple tension test. They include yield strength, ultimate tensile strength, percentage of elongation, and also some more properties will get from this yield strength. Will tension test will make use of those properties and will try to relate these to this. So that is, in tension test, the specimen is axially loaded. So like I already told you, so we know the specimen in case of simple tension test, it is subjected to only uniaxial load, that is only tensile load. But if you take a practical system, it is subjected to either bending moment or twisting moment or maybe combination of loads. We have seen some examples in the previous slide. A power screw, a overhang crank, or a bolted connection which is used in the bracket. So they are subjected to combination of test. But whereas our tension test will give you the experimental results for only axially loaded member. So that means how I can relate these two now. So that is done through this elastic theories of failure. So theories of elastic failure will provide a relationship between the strength of a machine component subjected to a complex state of stress with the mechanical properties obtained from the simple tension test. So that means, so now these elastic theories of failure will provide you that relation, the relation between the complex state of stress in a member which is subjected to complex loads to the properties obtained from the tension test. So now with the help of these three theories, the data obtained in the tension test can be used to determine the dimensions of the component. So irrespective of the nature of stresses induced in the component due to complex loading. So that means, so this is what we discussed in the previous point also. So in case of simple tension test, our nature of stress is uniaxial stress and the load is only axial load. So we get only the properties for that uniaxial load. But if we take a combination of stresses, the nature of stress maybe it need not be always tensile. It may be bending, it may be twisting, or it may be some other thing. So whatever it may be the nature of the load, in case of a complex state of stress, so still we can relate those complex state of stress to these material properties using these theories of failure. So if you take, there are several theories proposed, each based on different types of analysis or analogy. Hypothesis is nothing but some with some type of analogy. So that means, so when a component is subjected to different kinds of loads or combination of loads, some will assume the material may fail because of the maximum normal stress. Some theories will assume that the component is going to fail because of the maximum shear stress in the component. Some may assume that the component may be failed because of the maximum strain in the element. Similarly, maximum strain energy in the element or maximum distortion energy in the element. Like that, based on some hypothesis, so there are several theories are proposed. Out of those several theories, generally these five are the basic theories of elastic failure, which are going to use in designing the machine components when they are subjected to complex loading. So in that, the first one is maximum principal stress theory, which is also called as Rankine's theory, because this was first designed or defined by this Rankine. So that's why it is called Rankine theory also. And this theory is based on the maximum principles theory. The name itself suggests that it is based on the failure criteria based on maximum principles stress theory. Then you have maximum shear stress theory, which is attributed to the Coulomb, Tresca, and Guest. So these three people are worked on the stress. So the name itself here, this one is also suggests that the maximum shear stress theory will depend upon, or the failure criteria for this maximum shear stress theory is based on the maximum shear stress induced in the component. Similarly, you have a distortion energy theory, which is attributed to Von Mises and Henke. We'll call this one as Von Mises and Henke theory also. Here, in this theory, the distortion energy is the criteria for the failure. Distortion energy is taken as the criteria for failure. Then you have maximum strain theory. So that means, actually it is, okay, even though it is maximum normal strain theory, you need to say it is maximum normal strain theory. So here you have a maximum principal stress theory, which is also normal stress, and maximum normal strain theory. So there may be some similarity between these two. So that because here this Rankine is assumed that the failure is dictated by the maximum principal stress. So then these people, the Saint Venant, what he thought that why it is only the maximum principal stress theory, maximum principal stress will dictate the failure, why not the strain? So then he considered that approach, and then he designed or he defined another theory which is called maximum normal strain theory. Similarly, one more theory is there, why it is only based on the distortion energy theory, why not it is on the total strain energy. So this height is defined one more theory which is called maximum total strain energy theory. That means here, whatever theory it may be, so here whatever may be the maximum principal stress or maximum shear stress or distortion energy or maximum normal strain or total strain energy, so these are all because of the combination of loads. Then we need to relate these things to the data from our simple tension test. So however, here even though you have five theories, out of these five, these two are not going to predict. So even though they define the failure theories based on some criteria, this one is the maximum normal strain criteria, and this one is on the total strain energy criteria. These are not, if you implement these failure theories practically, they are not predicting the failure properly. So that means these theories are, even though they existed, they are only for academic purpose. So in practice, if you design the component based on either maximum normal strain theory, either total strain energy theory, the component is not going to withstand the given load. So that means the results, whatever results predicted by these two theories, they are not accurate. So that means, so these theories, even though they are only for academic purpose, they won't use in the practical use because the results of these theories are not accurate. So that's why we are not going to discuss about these two. Only thing is we'll discuss about only these three failure stresses. So which are very important in the practical aspect also. So we'll discuss only these three. So now we'll take those failure theories one by one. So first we'll take a maximum normal stress theory. So like I said, this theory is credited to W.H.A. Rankine. So he was the person first defined this theory. So this is credited, this failure theory is credited to Rankine. That's why it is also called the maximum Rankine theory also. Rankine theory or maximum principal stress theory. So then according to this theory, what is the failure criteria? So here this theory states that the failure of mechanical components subjected to either biaxial or triaxial. So why here only biaxial or triaxial is written? Why not uniaxial? In case of uniaxial, we already done it. So general, we already know the design equations. No need to use any failure theory in case of uniaxial state of stress. Only in case of biaxial or triaxial, you require failure theories so that you can relate the properties in the uniaxial state of stress, that is in the simple tension test, to the actual condition. So that's why we are using here only biaxial or triaxial state of stress. So according to this theory, the failure of mechanical components subjected to either biaxial or triaxial stresses occurs when the maximum principal stress reaches the yield or ultimate strength of the material. So that means, so when a component which is subjected to a combination of loads, then I need to compute what is the magnitude of the principal stresses in the component. So then what we need to do is, if it is a triaxial state of stress, you have three principal stresses, that is sigma 1, sigma 2 and sigma 3. If it is biaxial state of stress, there are only two principal stresses, that is sigma 1 and sigma 2. So now we need to compute those three, then we need to arrange. Generally, we'll take the sigma 1 is the highest one, then sigma 2, then sigma 3. So if you arrange all the principal stresses in a descending order, that means first I'll write the highest one, then next highest, then the lowest one. So then in that I need to identify the maximum principal stress, means the principal stress which is having largest magnitude. So then I'll take that, and if I compare the value with the value of that maximum principal stress with respect to yield strength or ultimate strength. Why we are using again two here? Because yield or ultimate. So depending upon the material, so whether you are using a ductile material or using a brittle material. In case of ductile material, we need to take yield strength as the failure criteria. In case of brittle material, we need to take it as a ultimate strength. That's why I need to compare this principal stress to the yield strength or ultimate strength. If the magnitude of this maximum principal stress exceeds either the yield strength or the ultimate strength of the material, I can say the component is going to fail. As long as this maximum principal stress is within the or less than the yield strength or ultimate strength of the material, we can say that the component is going to be safe. That means that design is safe. So that means in order to design the component, now your design equation will be, your sigma 1 should be equal to yield strength or ultimate strength. That is going to be your equation, design equation for based on this Rankine's theory. So that's what I written here in the slides. If sigma 1, sigma 2, sigma 3 are the three principal stresses with descending order, that means sigma 1 is the highest, next highest is sigma 2 and next highest is or out of these three the lowest is sigma 3. This theory says that to avoid failure, your sigma 1 should be less than SYD or SUD. So SYD means yield strength in tension. So yield strength in tension, and SUD is nothing but yield strength or ultimate strength in tension. So if the material is brittle, we'll use this one. If the material is ductile, we need to use SYD. If the material is brittle, we need to take SUT as the failure criteria. So or under. So here, if I arrange something like this, sometimes we may get, it need not always all these three principal stresses are positive values. Sometimes you may get negative value also. Since I am arranging in the order according to in the descending order, this is going to be there will be sigma 3 is the lowest stress, and there is a possibility of negative normal stress or negative principal stress sigma 3. So then if this is the highest value, then I have to use the other criteria also. That is, if I want to design for only the tensile strength, but here the negative stress is going to be the maximum, then I need to use the criteria to design based on the compressive strength also. It need not be only on tensile strength. I need to consider the compressive strength also. So then in that case, suppose if this is the criteria, that means out of all these three, if I want to design for a compressive strength, then I need to choose your sigma 3 less than or equal to minus SYC or minus SUC. Again, depending upon the material. This is for the ductile material and this is for the brittle material. So these are the equations if I don't use factor of safety. So sigma 1 is equal to SYD or SUT, or sigma 3 is equal to minus SYD minus SUC. Why I am using SYC negative? Because your sigma 3 is here negative. If it is negative only, we'll use this equation. Otherwise, if it is positive, we have to use only this equation. So now in these equations, we are not using any factor of safety. If I want to introduce factor of safety also into design equation, then okay, so I can write the failure theory something like this. So the design equation based on the maximum principal stress theory can be written as sigma 1 is equal to either SYD by Fs or SUT by Fs, where Fs is the factor of safety. So I can design the component like this. So similarly, when the maximum principal stress is a negative in magnitude, so that means if it is a compressive stress, you need to use these equations. So that means in that case, you need to consider the compressive strength. So, but here, this is the important point what we need to remember. Experimental investigations suggest that maximum principal stress theory gives good predictions for brittle materials. That means, so whatever theory proposed by this Rankine, this is predicting the results properly, or whatever results predicted by this principal maximum normal stress theory or principal stress theory. So they are predicting the results properly in case of only brittle materials. So they are not, however, it is not recommended for ductile materials. Why it is not recommended? Because the results whatever they are proposing here, whatever results they are predicting for ductile materials, they are not matching with the experimental results. That's why this normal stress theory, maximum normal stress theory or maximum principal stress theory or Rankine theory, whatever it may be, so it is not applicable or not suitable. I cannot say not applicable, but not suitable for ductile materials. So in that case, if I rewrite these equations, I need to eliminate this. So sigma 1 is equal to SUT by Fs, sigma 3 is equal to SUC by Fs. So like that we need to take. So only in case of brittle materials only, this theory is predicting the failure properly. So therefore, always we need to remember this point. So that means whenever if you want to use this maximum principal stress theory or maximum normal stress theory or Rankine theory, so you make sure that you need to apply this one only for brittle materials. So even you can apply it for ductile materials also, but only thing is in case of ductile materials, whatever predictions made by this Rankine theory, they are not good or they are not accurate enough with the experimental investigations. So that's why, so in most in practical cases, this theory is used for only brittle materials. So next, if I want to talk about, okay, so how I can identify, since it is a biaxial or triaxial state of stress. So now, suppose if I take a biaxial state of stress, how I can directly define, or how I can define the failure envelope for this theory. So for that, simply I need to take these equations, these failure equations. If I plot these failure equations on sigma 1 and sigma 2 graph, then I'll get the failure envelope. So this is the failure envelope for this maximum principal stress theory. So here it is a rectangle, a sphere. So even though it is sphere, but it is the origin is not located at the center. Why it is? Because if you see, this distance is more when compared to this one. So the reason for that is, for most of the brittle materials, the ultimate strength in compression is more than the ultimate strength in the tension. So that means your SUC value is greater than SUT. SUC is greater than SUT. So that's why you are getting like this. Suppose if SUC is equal to SUT, obviously this is going to be exactly at the centroid of this pair. So, but here that is not the case. In most of the brittle material, if you take, only in case of ductile material, I think we already discussed that also. In case of ductile materials only, yield strength in compression is same as yield strength in tension. For brittle material, that is not the case. SUC is not equal to SUT. Of course, actually it is SUC is greater than SUT. So then that is that you can observe here from this diagram also, failure envelope also. So this distance is more compared to this distance. Okay, now how I got this one as something like this. Now to design the failure criteria, so then what I need to do is, first I need to take this one as my equation, sigma 1. So in case of biaxial state of stress, we have only sigma 1 and sigma 2. You don't have sigma 3. So in case of biaxial, in case of triaxial, you have all the 3. But in case of biaxial, we will take sigma 3 is 0. If sigma 3 is 0, one of my failure equation is, if I take it is a brittle material, so I am disregarding the yield strength. So your failure equation is going to be sigma 1 is equal to SUT. So this is sigma 1 axis, I will take something, horizontal is going to be the sigma 1 axis, and vertical axis I will take it as sigma 2 axis. So now, if the condition is, if sigma 1 is equal to SUT, so that is the limiting value for the sigma 1. If the sigma 1 exceeds SUT value, the material is going to fail. If it is less than that, it is safe. So that means if I draw this equation, sigma 1 is equal to SUT, that is nothing but I will get a vertical line, something like this. This is the line whose equation is sigma 1 is equal to SUT. Then suppose sometimes I may have a chance of these two are also equal. Sigma 1 is equal to sigma 2 also. In some situations, I may get both the principal stresses are of same magnitude. Sigma 1 is equal to sigma 2. If that is the case, now if my failure equation now it is sigma 2 is equal to SUT. So then on sigma 2, if I draw another line, so this is the line which indicates that, or the equation of this line is sigma 2 is equal to SUT. And this line equation is sigma 1 is equal to SUT. So then you may have always need not to have a only positive stress. Sometimes you may have negative stress also. In that case, anyway, but in case of biaxial, you don't have sigma 3, you have only sigma 1 and sigma 2 only. So then in that case, your failure criteria is your sigma 2 is equal to SUC and sigma 1 is equal to SUC. If that is the condition, since it is a negative value here, sigma 1 is equal to SUC means this is the line whose equation is sigma 1 is equal to SUC. Of course, minus SUC here. And then this is the line whose equation is sigma 2 is equal to minus SUC. So then, see, if the region or if the point lies beyond these lines, then it is going to be fail. Suppose I have a point here, or maybe here or here or here. So then, if your design point lies beyond this one, so that means this is the region which is bounded by all these 4 equations. This is the region bounded by all these 4 equations. So therefore, this is going to be your failure region or safe region. Sorry, not failure region. This is the safe region, and this one what we'll call it as the failure envelope. So that means the safe region is enveloped by this one. If your design point crosses this envelope, your component is going to be failed. So therefore, in case of this maximum normal stress theory, your failure envelope is a rectangle or square. I can say it is a square or rectangle. If your design point, that means if I computed the principal stresses for a component, then I got sigma 1 is equal to some value and sigma 2 is equal to some value. If I design that one, so that means let us say sigma 1 is some 100 MPa, sigma 2 is some 50 MPa. If I got that, so first I have to mark sigma 1 is equal to 100 MPa and sigma 2 is 50 MPa. Then the point corresponding to these two values is like this. So that means this point lies within this region, within the failure envelope. So therefore it is going to be safe. But suppose if I take, if the stress is something like a 300 MPa, sigma 1, so then my point comes here, that is the case, it is going to fail. Means your design is not correct, or your component is going to fail for the given loading. So like that you can decide. So geometrically also you can decide. So once you construct this failure envelope, if your design point lies within the failure envelope, your component is safe. In any quadrant, it need not be in first quadrant, it may be in second, third or fourth quadrant, whatever may be the quadrant, you need to make sure that your design point should lie within this failure envelope. If it is goes beyond the failure envelope, your component is going to fail. So this is how you can design or you can define the failure equations in case of this maximum normal stress theory. Suppose if I want to introduce factor of safety also into the equation. Here this is a failure envelope I got without factor of safety. So now if I introduce factor of safety also, I'll get one more square box, something like this. So this is this line equation, I'll take it as SUT divided by Fs. So this similarly, this is also SUT by Fs, and this is minus SUC by Fs, and this one is minus FUC by SS. That means whatever offset you are doing it, that offset distance is because of your factor of safety. So then, if you use factor of safety, then your design point should lie within this boundary only. So if you fall outside, then as per your factor of safety, that means it is violating your factor of safety. So you can say that the component is not safe. Okay, so this is how we can discuss about this Rankine theory or maximum normal stress theory. But only important point what you need to remember is this theory will predict good results in case of only brittle materials. So you cannot use this one for ductile materials. So then if I cannot use this theory for the ductile materials, then what is the theory I need to follow for ductile materials? That we'll see next slide. So that is the next criteria or next failure theory is maximum shear stress theory. So first one we are taking it as maximum normal stress theory. Then the second one is maximum shear stress theory. So like I already told, this theory is credited to Coulomb, Tresca and Guest. So this theory is also called as Tresca's and Guest theory also. So they will call it as maximum normal stress theory also. So now according to this theory, how we can define the failure? So this theory states that the failure of mechanical components subjected to either biaxial or triaxial stresses occurs when the maximum shear stress at any point in the component becomes equal to the maximum shear stress in the standard specimen of tension test when yielding starts. So that means here, see, like what we discussed in the previous slides, so we need to relate the state of stress because of complex loading to the results of tension test. So that's what he written here in this also. So here he is relating the state of stress in case of biaxial or triaxial stress system. The failure will occur when the maximum shear stress in case of either biaxial or triaxial state of stress is equal to the maximum shear stress in a simple tension test. So that means we need to compute the two things here. So you need to compute what is the maximum shear stress in case of a simple tension test, and that too when you will get that maximum shear stress means at the yield point. So that means based on the yield strength only you need to compute what is the maximum shear stress in a standard standard specimen of simple tension test. Then you need to relate this maximum shear stress to the maximum shear stress in case of biaxial or triaxial state of stress. If these two are equal, so therefore there is a onset of failure. So that means the failure is about to happen. So therefore that is our failure equation or failure criteria in case of this maximum shear stress theory. So now if I want to write if I want to put this criteria into a mathematical form, how I can do that? So for that, first you require what is the expression for maximum shear stress in case of a tension test. So then you need to equate this one to the maximum shear stress in case of biaxial or triaxial state of stress. So now we'll try to compute what is the maximum shear stress in the two cases. One is in case of complex loading, what is the expression for maximum shear stress? In case of simple tension test, what is the expression for the maximum shear stress? So that is, okay, again I think it is repeating here. It states that any mechanical component subjected to any combination of loads will fail whenever maximum shear stress exceeds the shear strength of the material. That is, the strength of the material is nothing but shear stress at the time of yielding in the standard specimen of tension test. So the shear strength is nothing but the strength or the value of shear stress at the point of yielding. So we call that one as a shear strength also. So now, if this maximum shear stress exceeds the shear strength, we'll say the component is going to fail. As long as the maximum shear stress value is less than the shear strength of the material, then the component is safe. Here, the definition for the shear strength is nothing but the magnitude of the shear stress at the time of yielding in the standard specimen of tension test. These are important things. So you cannot take any specimen. So you need to take a standard specimen for the tensile test. Then you need to carry out the tension test on the standard specimen. Then at the point of yielding, you need to note down what is the shear strength. Okay, right. So that is the criteria for the maximum shear stress theory. So that means I want to find out what is the maximum shear stress in the specimen of tension test. What is the value here? So simply I write it as tau max is equal to sigma 1 by 2 or SY by 2. SYD by 2. How I got this SYD by 2 or sigma 1 by 2? So I said it is a simple tension test. So in case of simple tension test, it is a uniaxial loading. We know. So simple tension test, a component which is subjected to only axial loading. So it is sigma 1. Our load is tensile load. So let us take if the stress induced is sigma 1 only. So since you don't have any, if you take a normal stress on any plane here, you have only normal stress, that is a sigma 1. You don't have shear stress. Therefore, each cross section is going to be principal plane here. So the magnitude of the normal stress on this principal plane, I'll call it as a principal stress. So therefore, your sigma 1, whatever stress induced because of the P. Suppose if I take the load as P here, your P sigma 1 is nothing but P by A only in case of simple tension test. I think you already done these calculations also in your lab experiment. So this sigma 1 is going to be your principal stress. So now, if sigma 1 is the principal stress, so that means if I show the state of stress for this case, sigma 1, I have only sigma 1 in this case. If I take any cross section, if I show the state of stress on the cross section, it is something like this sigma 1. So now, for this case, I need to compute what is maximum shear stress. So we already derived in the previous class, we discussed the expression for tau max is nothing but sigma 1 minus sigma 2 by 2. Sigma 1 minus sigma 2 by 2, where the sigma 1 and sigma 2 are the principal stresses in case of biaxial. So now in case of your uniaxial loading, your sigma 2 is 0 now. So your tau max is going to be only sigma 1 by 2. So then, since I know the tau max is only sigma 1 by 2, it should be equal to SYT by 2. Why it should be equal to SY by 2? So the failure occurs when, in case of simple tension test, so the failure equation is, it is SYT, sigma 1 is equal to SYT. Hello? Evarandi? Ganesh evarandi? నేను క్లాస్లో ఉన్నాండి, ఒక హాఫ్ అన్ అవర్ తర్వాత ఫోన్ చేయండి. స్టిల్ ఇందాక మీరు కాల్ చేస్తే నేను కట్ చేసింది, అందుకే క్లాస్లో ఉన్నాను నేను. ఓకే. సో sigma 1 is equal to SYT. So this is the failure criteria. But what is our equation for tau max? Tau max is sigma 1 by 2. So therefore, I can write that one as SYT by 2. So that means in case of simple tension test, the maximum shear stress value, or I can say this SYT by 2 is nothing but SYS, yield strength in shear. I'll write it as yield strength in shear. So that is the failure criteria. What is the failure criteria for us in case of this maximum shear stress theory? Tau max exceeds the yield shear stress at the yield point. So the shear stress at the yield point is sigma 1 by 2, which is nothing but SYS. So therefore, I'll take the yield strength in shear as SYS, which is nothing but SYT by 2. So or 0.5 SYT. So that's what I written here. Therefore, the maximum shear stress theory predicts that the yield strength in shear is half of the yield strength in tension. So that's what. So I've taken this one as SYS. That is SY stands for yield, S for shear. Yield strength in shear, it is half of sigma 1 by r, half of yield strength. So that's what we written in this statement. So maybe if you take some other failure theory, it will predict in a different manner. Only this is true in case of this maximum shear stress theory. SYT by 2 is the yielding shear strength for material according to this maximum shear stress theory. So if you take distortion energy theory, it may predict yield strength in shear is in a different manner. So that means different value for yield strength. But for this, in case of this maximum shear stress theory, this is the prediction by this theory. So that is your yield strength in shear is half of the yield strength. So that's what I written here. Yield strength in shear is 0.5 times SYT. Okay, now this is the case with respect to simple tension test. So now I'm able to find out the expression for the maximum shear stress in case of simple tension test. Now I want to relate this to the given state of stress, whether it may be biaxial or triaxial state of stress, so that I can predict the failure. So to do that, first I'll take a triaxial state of stress. That means three principal stresses are existed. That is sigma 1, sigma 2 and sigma 3. Then I need to first compute what are the shear stresses because of the sigma 1, sigma 2 and sigma 3. Then out of those three, I need to take the maximum value and then I need to equate this one to this maximum shear stress in the simple tension test. I'll get the failure equation. So for that, we need to calculate the shear stresses. So here we already know the expression for the maximum shear stress. If it is sigma 1, sigma 2 are there, sigma 1 minus sigma 2 by 2. This is the maximum shear stress in tau 1, 2 plane. And similarly, you have a maximum shear stress in tau 2, 3 plane. So that is sigma 2 minus sigma 3 by 2. And similarly, you have a one more shear stress in the third plane because it is a triaxial, means three planes are there. On the three planes, you have three different planes. You have having different maximum shear stresses. That is tau 1, 2, tau 2, 3, and tau 3, 1. So for tau 1, 2, it is sigma 1 minus sigma 2 by 2. Tau 2, 3, it is sigma 2 minus sigma 3 by 2. Tau 3, 1, it is sigma 2 minus sigma 1 by 2. So now, out of these three, I need to identify whether the tau 1, 2 is our maximum value, tau 2, 3 is maximum, or tau 3, 1 is maximum. So I need to identify the maximum value of all these three. Then I need to equate this one to this. So that is going to be our failure equation. So therefore, the largest of these three stresses is equated to tau max or 0.5 SYT. So that is the failure criteria for this. So now, okay, so but if I want to use the factor of safety also here, so then in that case, what I can do, this is our tau 1, 2, that is sigma 1 minus sigma 2 by 2 is tau 1, 2 is equal to 0.5 SYT. So or else I can write as SYT by 2 is nothing but 0.5 SYT. And if I want to introduce factor of safety also, I need to divide yield strength by factor of safety. So therefore, this is the failure equation if you want to introduce the factor of safety also into the equation. So this is only the one equation if I consider only tau 1, 2. So but or else, okay, if I further simplify this, so these two will cancel out each other. So I can write this one as sigma 1 minus sigma 2 is equal to plus or minus SYT by Fs. Why I am taking here plus or minus means, so for a ductile material, we can take the yield strength as plus or negative, both are same. Yield strength in tension is same as yield strength in compression. That's why we are directly using plus or minus sign here. So then this is about only tau 1, 2. Then what about tau 2, 3 and tau 3, 1? If I write the expression for tau 2, 3, so therefore this is going to be the failure equation. Similarly here, in this case also 2, 2 will cancel out. You will get only sigma 2 minus sigma 3 is SYT by Fs, and sigma 3 minus sigma 1 is equal to SYT by Fs. So these are the failure equations in case of triaxial state of stress, means all the three planes on all the three planes. So that means you have a triaxial state of stress. So but if you want to go for okay, so using these relations, we'll try to compute the dimensions of the component. So these are the failure equations. Based on these failure equations, we'll try to estimate the dimensions of the component. So now if I want to move to the biaxial state of stress, so then what happened to my stress failure equations or design equations? So in case of biaxial state of stress, this first equation will holds good. So no need to modify because you have both sigma 1 and sigma 2. So only your sigma 3 is 0. In case of biaxial state of stress, sigma 3 is 0, then your equations will become sigma 1 minus sigma 2 is equal to S by D by Fs, sigma 2 is equal to S by D by Fs, and sigma 1 is equal to S by D Fs. So these equations are modified as, in case of biaxial state of stress, like this: sigma 1 minus sigma 2 is equal to S by D by Fs, sigma 2 is equal to S by D by Fs, sigma 1 is S by D by Fs. So now if I construct the failure region based on these equations, it looks like this. So here, first, like I had said, sigma 1 is equal to S by D by Fs means nothing but this is the line. What you are going to get? Sigma 1 is equal to S by D by Fs. Or simply if I take factor of safety 1, so this is the line which will represent sigma 1 is equal to S by D. Similarly, if I take sigma 2 is equal to S by D, I will get line something like this. So then, if I take these equation which it is satisfied, and also I'll take a negative value. So negative value means sigma 1 is equal to minus S by D means I'll get this is the line. And similarly, sigma 2 is equal to minus S by D means I'll get this is the line. The line equation of this line is wow, everything is gone. Okay, right. So this is the line which whose equation is sigma 2 is equal to minus S by D, and this is the line whose equation is sigma 2 is equal to S by plus S by D, and this is the line whose equation is sigma 1 is equal to S by D, and this is the line whose equation is sigma 1 is equal to minus S by D. So now this failure envelope is similar to your Rankine theory or maximum normal stress theory, but so this we got using only these two equations. So you have an additional equation here in case of this maximum shear stress theory. That is sigma 1 is minus sigma 2 is equal to S by D by Fs plus one time and minus one time. So therefore, if I don't take factor of safety here, I'll get sigma 1 by sigma 2 is equal to minus 1. So or else, okay, if I want to plot this line on the sigma 1, sigma 2 graph, so this is the equation for sigma 1 minus sigma 2 is equal to plus S by D, and this is the line which will give you the equation for sigma 1 minus sigma 2 is equal to minus S by D. So now the region bounded by now all these lines is nothing but this is the region. So it is something like a hexagon, whereas in case of your maximum normal stress theory, it is a square. Now you have a hexagon. So here, this is the, if your design point lies within this envelope, then your design is safe, otherwise it is going to fail. Okay, so this is how you can plot the failure envelope for this maximum shear stress theory. So I'll stop at this point because we want to discuss if you have any doubts, then we'll move forward in the next class. So because these are the fundamental theorems again. So these are the important thing. Basically, fundamentally, they are important to understand so that you can apply these failure theories whenever you require in solving the problems. So maybe we'll continue this in the next class. This maximum normal stress theory. Okay? So before that, before closing this class, I want to have some doubts clarification session so that we can discuss the doubts. If you have any doubt, then we'll go forward. So, see now, okay. So if you have any doubt, then you can put that into the message box. So here 59 members are giving the attendance feedback, but always only 50 members are present in the class. Means some people are just giving the attendance and they are leaving. So it is not difficult for me to identify those who are leaving the class just after giving the attendance. So that is going to be problem for you if you do like that. So I can easily identify it is recorded here. I'm not going to see all those things. So why I am pressuring I am thinking that I need not pressurize you. So on your own, you need to attend the class. Just for the sake of the attending means it is not good for you also. Anyway, so if you have any doubt, we'll discuss. Then we'll close the class. If nothing, no doubt, everything is clear, then also we can close the class. First, I'll stop the recording.